going to try and talk really a bit more about some measurements and what one can study using neutrons in particular aspects. I won't try and cover everything. And so I'm going to try and give some examples that are perhaps a little biased towards nanostructures and interfaces. And I have some general information, but I see some of that has been presented already, and so I can go rather quickly through some of that. But first of all, I am coming from Sweden, although I am not Swedish. It shows how the community is actually very international. But the 13th of December is actually a special day in the Swedish calendar. We should be celebrating the feast of Santa Lucia, and it's one of these festivals that comes slightly before the Christmas holidays each year, and it's celebrated with carols and singing, and by having coffee with saffron buns. Uppsala is an old city with many traditions, but this is a Swedish-wide tradition. Actually, the picture of Uppsala, I have to admit, was not taken today. As some of you will see, you will guess from the time on the clock of the cathedral that it's not quite right. And also, those of you who know Uppsala will realize that the sun is actually, in this picture, almost due south, little bit towards the west, and was actually taken just after midday. So the sun does come up here. It's not very high in the sky. So let's move on, and I want to talk about neutrons and how their properties relate to scattering, but that can be brief. I want to talk about some examples, particularly related to interfacial structures and how we can tune what we look at, and some scattering from interfaces. These are going to be very pictorial descriptions. I'm not going to give you lots of theory. I almost worry about trying to give lots of theory, because I see in the audience there are people who do much more neutron scattering than I do, based at facilities, and perhaps if there are detailed questions on some of these topics, we might ask them to provide answers rather than somebody like me who's really a generalist in this area. So with that sort of introduction, let me just give you some idea. We've been doing experiments at various facilities, but I should also thank people who I've been collaborating with and who've been discussing some of these ideas. But the presentation I take the blame for, and I put this up now in case we run out of time later. So with that, let's try and talk a little bit about neutrons. And you've already heard what a neutron is. Almost half the universe is made up of neutrons by mass. And so we should know about them and we should use them. And these properties that they are neutral, they have spin, act like a magnet, that they are massive, even at rest, unlike photons, all determine their interactions with matter. And so they determine how we can use the neutrons in experimental studies. So as we saw, the charge is zero, they have spin and mass, and the scattering depends on isotopes of elements, not just on elements, and so it allows a good deal of possibility to select what one is looking at, and I will come into that a little bit later. So the consequences of these properties of neutrons are that they penetrate deep in many materials. Because they're uncharged, they don't just get scattered or absorbed at the surface. That you can also look at magnetic structures and magnetic dynamics, as we've been told. Because they're massive, they can often undergo inelastic scattering and exchange energy with samples, and this measurement of the exchange of energy allows us to study dynamics. But very particularly for many people, an important feature of neutrons compared with other available tools is that one can study light elements such as hydrogen and use isotopic labels. This use of labels and identifying materials that are made up of hydrogen and different isotopes of hydrogen is of particular advantage in many complex systems. And just to give you some idea of what is happening in these things, the velocity of a neutron with a particular wavelength is actually quite small, that the velocity for a 10 angstrom neutron is about 400 meters per second. So these inelastic effects change the velocity. It's very easy to measure that with simple timing circuits. So I want to move a little bit, just put this in a context. Many of our societal challenges that we face involve complex systems, that we've moved well beyond just wanting to investigate single crystals, perfect solid state objects. We're interested in systems that are formed of many components. We're interested in what happens at surfaces and interfaces. We're interested, for example, in biological materials. These all relate to the challenges that are associated with providing good health, providing energy for the future, even simple things like providing clean water come into these areas. And so being able to look at these complex systems is really important, and being able to look at materials, whether they're simple or complex, inside realistic conditions, when you apply forces, change temperatures, while they're undergoing chemical reactions, is really important. And so the power of neutron scattering is really that one can look at relevant materials in relevant ways, identify what particular components have structures, or even how they're changing with time or moving. And this is really a key advantage. And so I want to just give you a little bit of an introduction to scattering. If we think about how we normally see things with visible light, we may be making observations based on the scattering of light, such as from the droplets of water in clouds. We may also be seeing things by absorption of different colors. These depend on properties of materials. The scattering of light depends on the refractive index difference between the droplets and the surrounding medium, the air. the colors depend on absorption of particular materials, but it also depends on reflection, and that can be quite a complicated interplay of what is happening. So we're used to looking at things with light and inspecting them in various ways. Often we want to look at a small scale, and so you might ask, why do we use scattering? The tradition might be to use a microscope. So let's think about that. We have some convenient radiation source. We've been hearing about neutrons, and it provides interesting contrasts. We would shine that radiation at a sample. And if we have a microscope, what we would normally do is we would be able to put in a lens and build a magnified view of the object. And that's because it's rather easy with light to make lenses, compound lenses, series of lenses, so you can make microscopes. You can do this with as well, and there are limited moves to make lenses with X-rays. They go quite a long way now. We don't have so many lenses for neutrons, but if we have this system of shining light with a certain wavelength at a object, and we have a detector, we know what the lenses would do, and so we can calculate with a computer what the pattern of scattered light would be, and we can compare that with observations on a detector even without a lens. And really, this is what scattering experiments are about. So we can go on and think about the time correlations. I won't go into the details about this, but the important thing, if you're not so familiar with scattering experiments, is to remember that we're interested in analyzing the pattern of scattering that occurs at different angles, perhaps for different wavelengths. These can be unified into this variable that's called the momentum transfer of the scattering event, this quantity Q, and we can use that to model the scattering process. We're working, if you like, in what is called reciprocal space. Q has the dimensions of 1/, length, that if we measure at big angles, we're looking at small distances. If we're looking at small angles, we're looking at big distances. We can think of observing correlations at different values of momentum transfer, and the size scale for those correlations depends in this way on the reciprocal of the momentum transfer. And I hope the specialists in the audience will forgive this very simple introduction to the topic. And just to emphasize again how neutrons see different elements, I've plotted here some neutron scattering lengths, and for comparison, some X-ray scattering lengths. And sometimes people say that the neutron scattering length for different elements is random. The nuclear physicists would not like that statement. It's not, as you can see in this plot, quite random, but it is beyond the scope of this lecture to talk about the nuclear structure and how it will influence the scattering length. But you can see that one can observe these light elements like hydrogen, deuterium, carbon and oxygen just as well as one can see heavy elements. So this is really very important in designing studies for interesting systems. So that's a little bit more detail on these plots. I won't go into that now unless there are particular questions. And just to show you this, it's useful sometimes to use multiple techniques. This is in some ways a very commonly quoted picture. It shows taking a picture of a camera. It might look a little strange to do that, but this is a traditional camera that was working with film, and so the parts of it some people will be familiar with. There's a lens, but there are also spools for film, and with neutrons you can see the spools that would be made out of plastic and have the film on. The X-rays don't really detect the absorption from those very light parts, and you can see that it's a very complementary technique. But I'm not really going to talk about imaging. There are other people who will talk about imaging. I'm going to talk about scattering, but I'm going to really emphasize in this short lecture what we might think of as low resolution scattering, looking at large objects. And often it's useful to do that by thinking not about individual nuclei or atoms, but about average densities of these in particular regions. And so we will often work with the average of the scattering length density, because if we're looking at solutions, there may be a mixture that makes up a particular volume in a sample. But what's really useful is that we can take all ideas that are in conventional optics books, and we can use them to understand what we're seeing. And the only thing that we really need to know is how to calculate the refractive index. And the refractive index N for neutrons is calculated using this rather simple formula that the difference from 1, the refractive index, is equal to the product of the wavelength squared and the scattering length density divided by 2 pi. That's really very simple, and it allows us to use a large amount of the existing theory on this without actually going any further. But it's useful perhaps to think about what some of the values of this are. If you're used to the refractive index for light, you think of the refractive index of vacuum is 1, air is very close to 1, water is 1.33, glass maybe 1.55. But if we look at this difference and put in some of the values, you can see in this table that we actually have differences that are really very small. They're also different in that the refractive index is often slightly less than 1 rather than slightly bigger than 1. Related to the properties that we spoke about earlier, that the neutron doesn't interact strongly with most materials. And that's why the differences are very small. But it does mean that typically scattering is low, and that the optical effects, such as total reflection, that was mentioned in the last talk and is used in neutron guides, but is also used to study materials, occurs for most materials at extremely low angles, less than 1 degree grazing instance. And we'll come on to some of those studies in just a few minutes. So this gives you some idea, but we can calculate these properties for all sorts of materials. There are tables with scattering lengths, and so if you know a chemical composition, you can calculate a scattering length density and you can calculate refractive index. And this will allow you to make models of materials. I would just like to say one other thing about this, that the magnetic contrast that's been mentioned, it's actually very useful. It's a fairly small change. It's you can consider it as a change in the scattering length for a nucleus. It will depend on the field and as to how this is observed. Let's just give you this simple idea that you can combine the scattering length from the nucleus and the scattering length from the magnetic component, and it will either be plus or minus depending on the spin of the neutron. So I won't go into this further, and I see that we have many experts on this in the audience, and so we will leave it at that, but it's a very useful concept to bear in mind. But I want to spend most of my time talking about some examples of experiments where nanostructures and interfaces come together. Interfaces are really very important. They're where things happen, whether it be as catalysts for reactions, whether it be viruses interacting with cells and infecting people. This has become hugely important studies, and the proteins that relate to this are hugely important at the moment. It can be many other things. It can be lubrication processes. So the interfaces are really very important, and so we should always think about them when we're considering many of our everyday materials. And I want to do this, and just one other thing I should mention is that the interfaces we can think of as just being simple structures, and some people will be able to model adequately as just uniform planar structures, but they're often three-dimensional, and I want to show you that actually thinking about them as three-dimensional objects is also important. Let's first of all think about reflection and just what happens if we have layers on the ground. If we go outside on a damp day, as we have here at the moment, although the water's mostly frozen in Uppsala this morning, we can see perhaps where some oil has dripped from some poorly maintained vehicle. We see a drop of oil on a damp road surface, and you can see the pattern of light that comes with reflection of different colors at different angles, and that's because you have interference of light that is reflected from the different surfaces, and you get the different wavelengths constructively interfering at different angles. And so if we see things like that, we can think about understanding the thickness of the films that we have. In the same way, we could do the experiments with a much shorter wavelength. And I'm going to talk about neutrons, one can do some experiments with X-rays, and we come in at a very low angle rather than a high angle, and we bounce a beam off a surface, and we can look at molecular structures at the surface. If we analyze the intensity of the reflected beam as a function of angle or of wavelength. And this is really a very simple experiment. There are some challenges in doing it well, and I will just show you a few of these things. But if we want to look at the structure of molecules, whether it be proteins, other materials, lubricants, we can look at them at a surface, and I will show you some examples of this. The important sort of concept relates to the ideas that I mentioned about using isotopes. If I have some molecules that are sitting at a surface, and if I, for example, calculate the scattering length density of a crystal substrate such as sapphire and the scattering length density of D2O, we have something like 5.7 times 10 to the minus 6 angstrom to the minus 2 for sapphire. We have a little bit higher for D2O. If I have some normal hydrogenous amphiphiles binding at a surface, I will see some very strong contrast if I have sapphire and D2O. If I put the surface against H2O rather than heavy water using the normal isotope of hydrogen, I will just see something that is looking a little bit different, but I will have some contrast perhaps between the slightly different regions of polar head groups in these amphiphiles and hydrocarbon tails. And so a combination of measurements using different contrasts that you can make with neutrons is really valuable in getting details of structure. And I want to just give you a little bit more information about that because it's perhaps important to get some sort of scale of what one's looking at. Now, actually, a lot of the amphiphiles that one's looking at are much thinner than 100 angstroms. But if I just do a simple model calculation, you can see that we actually have a separation of these different scattering depending on the contrast that we have. This is just a uniform layer. The fringe spacing really tells me about the thickness of the layer, but actually whether the change is big or small, and whether it's a step up or a step down in contrast will give me the position of the first minima. The phase change makes a large difference. So full modeling of these curves is really important, but perhaps also important is to realize that the reflectivity drops from the total reflection down to very small values, 10 to the minus 5, 10 to the minus 6. It's quite small values of momentum transfer. And so this is why we need bright sources and low backgrounds to make good measurements. It's a very simple experiment, but you need high quality instrumentation and high quality design of your experiments to do this. And just to give you a little bit more information. Had a slide already talking about some penetration of the probe into the sample. And this is actually very important if we want to start looking at structures that are more complicated than just simple layers at a surface. We're interested in how rapidly the radiation decays as it enters into the medium. And this is something where the theory is fairly straightforward. I won't go into the detail. You'll find it in many of the textbooks. It's the same for neutrons and for X-rays. There is just one thing I would caution you when using this. So this is the attenuation length, the distance which the radiation will drop off 1 over E as the varying with angle ratio of the angle of incidence to this critical angle for total reflection. This quantity mu is described as an attenuation coefficient. The textbooks on X-rays often describe it as an absorption coefficient. It's actually quite important for neutrons. Often the attenuation arises as much from scattering as it does from absorption. And so it's important to calculate this mu from the total cross-section rather than just an absorption. And this is something that people have often not always remembered when they're doing this. It's also quite important to think about instrumental effects that I will show you that very briefly. Typically, if we're measuring with a spread of wavelengths, we will actually then have a spread of critical angles, and this can also make quite a big change. And this change in the depth of penetration is several orders of magnitude, and that can be quite important when you're modeling reflectivity and modeling scattering near interfaces. So it's been a very quick and general introduction to some of these topics. Let me now give you a few simple examples. And the first one that I was going to talk about is a study of lipids and lung surfactant. And this is something where we can spread a layer of relevant systems. Now, we can actually study real lung surfactant, but that's a very complicated mixture. What we've mostly been looking at is looking at components of this in simplified mixtures, and I will give some examples. And this is actually a picture of one of the first experiments in this sort of area where we could just spread a layer of lipid on a Langmuir trough. And because we were starting, we just put the whole assembly in a glove bag and put some quartz windows in so that we could bring the beam in and out. We now have chambers that can control the environment a bit more systematically. But if we have these lipids and we look at them at a surface, lipids are amphiphilic molecules. A lot of the natural lipids that we're interested in have water-soluble groups and oily hydrocarbon components, often two of them, and so I've drawn them schematically, something like this as a polar group with two tails, as known in the jargon, and they will sit at a wet surface. If you have them at a surface that's polar and you surround them with water, they may well form a bilayer, and they will form membranes. So they will form components of cell membranes. But these types of molecules are also things that keep the surface of the lung wet and lubricated, and so they're really very important in many biological systems. And there's quite a variety of chemistry of these. I won't go into all of the details, but we've looked at a few of these, and I'll just show you something about a particular type of molecule. This has got a polar head group, phosphocholine head group, and we have two hydrocarbon tails, but they're different, and there is a carbon-carbon double bond in one of the tails, and this double bond has several consequences. It disrupts the ordered structures, and so this tends to make the layers much more fluid, but it also makes it susceptible to damage, because the carbon-carbon double bond, it tends to be more reactive. But we can look at the structures of these, and in particular we had materials where we could label different parts of these molecules. Label this part labeled 1, which is the end beyond the double bonds, and we could look at the other tail and we could make different molecules with these labels, and we could see what is happening with these separately. And we could look at how these change when we do an experiment where we actually add controlled amount of ozone. This is actually a very small amount of ozone. You only need to look at the amounts that you get around printers and copiers, less than a part per million. You will start smelling it, and they will actually start giving you respiratory distress. And you can see why. If we look at the part that was labeled 1, it is lost within an hour. We can look at the decay of that and the decay of the other part, and we can see that they're lost from the surface different rates. We can actually see some of what's happening just by monitoring the surface energy or the surface tension, but we don't get the full molecular picture of what is happening. And so the neutrons have allowed us to see that you lose this particular part of the molecule rather quickly, with significantly less than a part per million of ozone in the air. So that's one example. I would like to just talk a little bit about some other examples. So solid particles, do they absorb, do they order? And it's useful, as with the lipids, to look at some model systems. And here is some example of polystyrene latex. It's a charge stabilized model colloidal system, nanoparticles in water. But as you can see, you get nice iridescent colors from the scattering and reflection of light, and so you get this nice color pattern that can be seen, and it actually seems to form on the walls of vessels first of all. But let's just look at this. We can do scattering experiments, in the same way as we would do reflection experiments. We can inject a sample next to a solid surface. And when we do that, this was for these particles in against a sapphire surface in D2O. And actually, it's very interesting because when we do that, the 5 degrees. There is almost no intensity seen in the reflection here. We are seeing only the scattering. And we see a very regular pattern of scattering. And so this is really telling us that there is a lot of ordering when we do this. I might say that we've found that we can get better scattering patterns, more intense scattering patterns, depending on how we flow the material against these surfaces. I won't go into the details of that. If we convert this into maps of momentum transfer in 2 directions, you can see that there is a very regular pattern of peaks with alternating intensity. This we can see just by taking cuts along here. This is telling us that actually over quite large areas, we're getting very uniform scattering, uniformly oriented scattering. I will come on to that in a bit more. So we can form very highly ordered arrays at surfaces, and that can be rather important when you want to use these to make photonic devices and things like that. But in order to understand that in more detail, we actually want to move away from just doing reflection to looking at point-like beam and looking at the scattering in grazing instance geometry. And we've done that against different surfaces, and you then see that you have a spot pattern, and actually we can understand the alternating intensity that was observed when we just looked on a reflectometer, because we're cutting through different peaks in the scattering pattern with a slit-like geometry on the reflectometer. And so it can really be very important to look at these. Now, the problem is that the peaks are actually quite low intensity, and actually modeling these peaks is really quite difficult. What we can do is we can look at the ratios of different peak intensities and see how they vary as a function of the instant angle. And we can compare them against different structures. Unfortunately, it doesn't really tell us directly from this how far the particles are from the surface. We would like to identify that, but we're not quite sensitive enough, and that's why we would like even brighter sources. But if we compare this also with other laboratory techniques, we can get information about the structure and how far they are from the surface. But with the neutrons, we can actually do something rather simple. We can turn that reflection scattering cell around so that we can look straight through the sample, and we can actually look at this. I just skipped through some of these points rather quickly, that we can see what happens when we have a different size beam just going straight through the sample. We can see that when we're averaging over 2 millimeters thickness, we see almost a ring pattern with a little bit of texture. We start seeing a lot of texture when we get down to a 1 millimeter beam. So when you start looking at this, you can see that in the bulk of a sample, you will actually have smaller regions that are uniformly ordered. And when we look at the surface, we have large areas that are uniformly ordered. I won't go into all of the details, but this shows you the power of neutrons, that we can actually use a grazing instance study to look at controlled depths near a surface where we're just exploring hundreds of nanometers or micrometers, and then we can look right the way through the bulk and look at samples of considerable thickness. And I think because we're running a bit late, I will stop at this stage. I won't give you much more. I should just say thank you for your attention. Thank again all of the people who have been involved in some of these studies, and I will be happy to take questions.